about 6 years ago, we got together in Scotland, not knowing one another, masons, large stonemasons, plasterers, from around the UK and from Ireland. So it's always been a British and Irish thing. And we realised that there were more of us doing it than we thought, and that we all sincerely believed that this was the right thing, and that what we were doing was, well, the wrong thing, actually. I mean, not to mince words. And that just gave us the confidence, us getting together as a group, to start shouting about it, really, and to start saying, well, look, we think this is right, and we're all conservators, we all believe in like for like, but we've spent 40 years not working like for like, but pretending that we have been, and that caught fire, really. We started organising big events where lots of us were talking, and everyone was coming, and it's been this very much a grassroots sort of upward pressure, but with a very positive response from Historic England, from Historic Scotland, the top level, the research level. So it's been this very much an alliance of grassroots craftspeople and the supervisory body, the research teams of Historic England and so on. So yeah, it's worked very well, but anyway, that's just a little introduction, and in the course of that, of course, when we started saying this is what we think should be done, obviously we hit a lot of resistance from people, from vested interest, vested intellectual interest, of course. And please understand, I'm not blaming or criticising anyone in anything I say. We have all done what we've done with the best of intention, and I have done the same. I have used all these materials myself, obviously I have, and always with the best of intention. So please, nobody take any, I'm not blaming anyone. This isn't a blame game, but we've got to get this right. We've got to reassess what we do and how we do it. And I believe that to be a benefit not only to ourselves as craftspeople and as conservators, but obviously to a benefit to our historic fabric. So yeah, just a little introduction. And this moves, does it? Which one?
The other side, this one.
Okay. Okay, so that's just a very brief introduction. This is, well, it's there because I love that little church. It's in Normandy, in the village of my former apprentice, who was French, Norman French. But earth line built, hot mix line pointed, the normal story, but that's just an introductory thing, so it's not. Thank you. Well, I'll take us to that now. Yep. Okay. If we can maybe just start with a basic principle, which I hope informs everything we're talking about. This is a Royal Institute of British Architects publication after the Second World War, very much aimed at building a better world after the horrors of the Second World War. But so it's a wonderful book to read because of its ethos, its attitude. But the technical evidence does not point to shortcuts in the achievement of good building. It points consistently to the discovery by scientific means of the rationale of established building traditions, which should be altered only with the full knowledge of the consequences. That's the key line, only in the full knowledge of the consequences. I don't want to talk much about natural hydraulic lines and that sort of thing at this moment, but I have to say we are using a material the consequences of which we do not know. The main outcome of the Historic England research, which should have been done 25 years ago into the properties of NHLs, the key headline is that they keep gaining strength. For a period we do not know. Nobody can tell us, no producer can tell us when they stop gaining strength, and they're gaining strength and lowering porosity in that whole process all of the time. So that's just one thing. And I in the course of all this research, I should just say, we've done a lot, people know, I've researched through hundreds and hundreds of old texts online, going back the last 2,000 years, from France, from Spain, from Britain, from, well, wherever I can understand and get the language. So what I'm saying is based on largely on that and going through building accounts, so direct documents of real buildings historically where they're listing materials and so on and so forth. But anyway, I don't need to dwell on this, but this is what we're talking about: traditional building fabric that is capillary active in most of its forms. So that the materials we use need to be at least as capillary active as those materials to keep them dry. Not vapor permeable only, capillary active. This is the conflict we have in Britain at the moment. We've got many conservation products that are vapor open, capillary closed. If they are capillary closed, they will not work. Yeah? That's a difficult argument in the UK.
What do you mean by capillary, sorry, what do you mean by capillary closed?
Well, they put in ingredients that disrupt the pore structure so water will not move out by capillary action. Typically it will stay there.
And what is vapor permeability?
Well, the movement, the idea that a water vapor molecule will pass through a porous material, which in and of itself defies the laws of physics. But yeah, and we've got all afternoon where we're demonstrating. I'm very happy to field any questions. Yeah, but so this is what we're talking about, not the resistance of the futile attempt to resist moisture, to manage moisture, but we need the right materials to do that. And our experience, as another example with NHLs, is most of the buildings that have been repointed or repaired with natural hydraulic lime in our part of in the north of England are permanently wet. Permanently wet. They're not drying. So anyway, that's a little bit about that. But to summarize, if you like, the conclusions of all that research we've done, and all that research obviously in parallel with my experience, was critical, I think, that I actually use these mortars, not just reading a book, but relating everything I see. But all I can say in truth is that I've seen very little in 2,000 years that does not make sense to me. But when I hold that up to what we've said for the last 40 years, since the lime revival, most of that you don't find in books historically. It's a different story, it's a different narrative, it's an invented narrative that is not the same, and often the rules are not only different, they're the polar opposite for the last 2,000 years compared to the last 40 years. So this is quite an important thing, but this would be my summary of what were the traditional mortars in a general sense, you know. So obviously earth mortars, very common over millennia. Clay-bearing subsoils, improved, and I still use that word, or otherwise, with well-tempered loam, improved with sand typically, in this case, to reduce the clay content, to reduce the shrinkage. Typically about 12% clay, a very high volume of silt, which I believe to be as important to the performance as the clay. Used for masonry construction, plastering, daubing, which is another word. Typically if you plastered with mud, it was called daubing in the UK. Floors, perhaps with additives, often with not. But more particularly, I would say, and a mortar that has been largely, certainly ignored by the conservation industry in the UK until recently, is an earth lime mortar that has a small, typically small, but not always a small, proportion of quicklime added to it, which transforms an earth mortar, which is not a bad mortar, but transforms it into a wonderfully workable, cohesive, adhesive, and much more water resistant mortar, but also very high in its capillarity, as a very optimal capillarity. And that's for the same purposes. And these mortars, most stone buildings in the United Kingdom built before 1800 were built with earth lime mortar. The bedding mortars are earth lime mortars. That is, in terms of historical time, there is no question the most common masonry mortar is earth lime mortar. It's not lime sand mortar, it's earth lime mortar. In terms obviously of volume, surviving volume, then we have a high volume of buildings built with lime sand mortar in the UK because they're newer. But if we mean in historical time, this is the key, and that is the typical Roman mortar of Roman construction and of Norman construction and all of these things. It is the most common mortar. But in most cases, I would say almost universally in the masonry trades, that you don't just leave that, although it is incredibly durable on its own. It's pointed with a very lime-rich mortar, and often a pure lime and hair mortar, or indeed a lime and limestone dust, typically mortar, or a stone, but always with more lime than aggregate. So and so on, and so those are very common. Then we come into the hot mixed air. Understand the definition: an air lime, a fat lime, a pure lime. They're all the same thing, but the current European nomenclature is that we should use air. And of course, historically, natural hydraulic limes were called water limes. So air lime, water lime. It tells you where they belong. Fat limes in the air, water limes underwater or underground, where fat limes will not set. Simple as that. Because they rely on carbon dioxide, taking carbon dioxide. But hot mix, and these displaced earth lime mortars for building in the UK after about 1800, not sometimes after 1850, it varies around the country. And of course then you've got a whole system that's built with hot mixed lime mortars, very lime rich, never leaner in use than 1 lime to 2 after slaking, never leaner. One of the biggest mistakes we made in the lime revival was to mix 1 slake lime to 3. That's a non-existent mortar historically. It does not exist. They are only ever, the leanest they are likely to be is 1 to 2, and they'll only be richer in lime than that, not leaner. And that is essential. It's why lime putty got a bad name in the UK and elsewhere. Not enough lime. And why we thought we knew better and thought, well, hey, let's ignore thousands of years of history and put half as much lime as they ever did into the mortar, and then wonder why it doesn't quite work. That's modern arrogance, isn't it? We know better. We do not know better in the case of lime mortars. We really do not know better. So, and they are all universal. I mean, I would hazard that 95% of building mortars in the UK until around 1910 were made by this method, by a hot mix method, and from quicklime. So them, and then putty lime. Now, shock horror, this was a shock to me. Putty lime slaked with minimum volumes of water, so very differently slaked actually to the way it tends to be today. I think I would call modern putty lime yogurt. Lime yogurt. Maybe Greek yogurt, to be fair, but that's about it. Lime putty, when described historically, is always described as being of a bread dough consistency. I think we can see that's a different material. And the difference comes from the method of slaking, as it does in all of these things. So, and that was used on its own as a mortar, not as a binder. Was distrusted through time as a binder. This is a shock. To me it was too. I didn't expect that. So until the 20th century, then it did become commonly used, but typically because they knew they were going to gauge it with Portland cement. And if you make a cement lime mortar with lime putty, it is beautifully workable. If you make it with hydrate, not nearly so workable. So, and it was used for the finest joints in stone ashlar, the finest brickwork joints, and for the finish coats on lime stucco. And that's what, when Vitruvius talks about laying lime down, it's to get rid of the lumps that haven't slaked, for them to slake. Because the purposes you're going to put it to demand that there are no lumps left, because you're going to use it for a fine finish. We're craftsmen, we don't want a lump scratching across the wall. It's as simple as that. There was no concept historically that it got better or matured. It was always to get rid of those lumps because of the purposes you were going to put it to demanded no lumps left in the mortar. This is a hard thing to get across, or to absorb, that notion, but it is absolutely the case in my observation. And I think you've seen the graph just a minute ago of all the samples from Scotland and around. Where was the lime putty? That much, yeah? In those analyses, the hot mix that much. So that's the difference. And then, so that's that point made. Yeah, okay. Lime and hair, but for common was roofing applications. But again, that was slaked and used immediately. In most cases, when they use lime putty, they would slake it and use it within a week, not 3 months. Their belief was the longer you laid lime putty down for, the weaker it became in its binding properties. And there is modern research that indicates that that is true, yeah? And you'll see that with the hot mixes. The bond within the mortar is completely different. It's a very tenacious bond within the mortar as you're using it, as you're making it. Very different. So it's not a bad material. I mean, if people want to carry on using lime putty on historic monuments, great. It's a very sacrificial material. But I think in masonry terms and craft terms, maybe a little too sacrificial, perhaps. You know, it lets more water in, particularly when it's too lean in lime. And then we've got hot mixed or sand slaked, moderately or eminently hydraulic lime mortars. And I would say right now that a modern NHL2 is not a feebly hydraulic lime. By historic definitions, by VCAS definitions, he would have called a currently available natural hydraulic lime to an eminently hydraulic lime, okay? Where that leaves NHL5, I don't know. But as you will see later today, in many of the brands, the NHL2s are the strongest, not the 5s. This is one of the problems. You don't know what you've got in that bag. But they were used underwater. Our blue lias, which was considered the hardest natural hydraulic lime available for engineering works, that was 72% free lime. There is no NHL on the... No, it's a geology.
Oh, it's not the brand?
No, it's a geology, yeah. And if they might use them underwater, but if they did, they would add pozzolans into that to consume the free lime. They didn't trust them on their own as an underwater mortar, but more likely they were used in very wet conditions underground, and that sort of thing. But I have to say, the evidence of all my research is that the only purpose for which natural hydraulic lime was the preferred binder in the UK, in Europe generally, was to make concrete. That was the only purpose that they preferred to use it for. So for those conservators, and I'm one of them in the room, we have to ask a simple question. Why have we spent the last 25 years covering our buildings with a material that historically and still at the end of the 19th century, they considered to be only appropriate to make concrete floors and concrete footings of buildings and rammed béton in France, rammed concrete structures, yeah? I'd leave that question in the air, all right? So, and then natural cement after 1796, but that again wasn't used for building. That would be, no mason would use that to build a structure with. That's far too hard, far too fast setting, but it was useful for waterworks because it does set underwater very quickly, and mainly for cast moldings. American engineers liked it for fortifications, but they were building these during the Civil War. They needed them built and strong from the moment they were built. They didn't have time to wait. But even then, they used hot mix mortars, generally lime rich, and they would gauge with natural cement to speed that initial set, yeah? Never use it on its own for that purpose. But they would often point with it on its own. And we are in the period where I believe we do need to consider cement lime mortars to be historic mortars, and that where they exist and where they're causing no damage, which they will rarely do, in my observation, a 129 or a 1312, 116 is a different matter, perhaps. We need to be working like for like with these materials. So in Tel Aviv, we've got very successful cement lime mortar work that is being displaced by other mortars. Why? The like for like material is cement lime. And a typical cement lime or a 129 has 66% of its binder is air lime. There is no natural hydraulic lime on the market that has that much free lime in it. And the other thing to say, as I will demonstrate later, the key issue with natural hydraulic lines, one of the key reasons they were never used for building unless they had no choice historically, is that they are an inherently variable material, not only between sources, but within the same quarry. They vary in strength all of the time from one day to the next. Portland cement, which is mineralogically, I mean, put it another way, a natural hydraulic lime is actually a weak cement lime mortar. That's what it is. It should be, in my opinion, be called a natural cement lime mortar, not a natural hydraulic lime mortar. But they are predictable. We know exactly what the strengths will be. We also know that a typical cement lime mortar will reach maximum strength after 3 months. Not after 10 or 20 or 30 years. We know pretty certainly that NHLs will gain strength for 10 years at least after they've been in a wall, and on it goes. We don't know. That's the whole point. We don't know. Isn't the basic rule of conservation, we don't use materials that we don't know the potential of, the consequence of. So we need to take these seriously. They are well-performing mortars, and they were designed to be exactly that, initially by the United States Bureau of Standards, who recognized the need for high free lime, as high a free lime content as you could get, but compromising with modern building technology and the demands of the modern building industry that did demand rapid early initial set. That's all it's about. They're often weaker than if you used a straight pure lime mortar. 1-3-12 is unquestionably weaker than a 1-3 hot mix lime mortar with no hydraulic activity at all. But of course, the hot mix will take more years to get to that strength. That's the difference. So, okay, I want to initially go through, forget all that, this versus that. What we actually need to look at is what actually are mortars for. You know, what does a mortar need to be to do the job that is asked of it? And so to look at historic understanding of that, so this, the first one, mortar ought to serve at least 3 purposes: to form a soft but gradually hardening bed, critical, soft but gradually hardening bed, to receive the various building materials, so that these shall obtain a uniform bearing, notwithstanding the irregularity of their surfaces. We would add to that now, a soft but gradually hardening bed is essential to the formation of the bond with the substrate. You need that to be, but I'll talk about that in a minute. In the second place, to prevent the passage of wind and rain through the joint. And even the United States Bureau of Standards, you know, you might think we're all cement lovers, always acknowledge that the mortar that will keep the building driest, that will resist the most mortar penetration, rain penetration, is a pure lime mortar. That is the one because it makes a proper durable bond that prevents the water getting in. But we'll talk about that later. And that the more hydraulic that mortar is, the less it will resist the penetration of water. Counterintuitive, but that's all to do with bond and the quality of the bond that is made. And lastly, to have adhesive and cohesive strength enough to bind the component parts of the wall into one solid mass. Not, as some engineers frustratingly say, even friends of mine, engineers who are friends of mine, the purpose of mortar is not to hold the stones apart, as they so often, it's to glue them together. I'm a stonemason. Why would you, if you don't want, you can build the wall dry, it can still be structural, but it won't resist the things we want to. So it is to hold them together, it's not to hold them apart. That gives quite a misleading impression of what mortars are for. And then if we move to 1964, Robert Boynton, American chemist, any work by his is fantastic, but mortar strength is often greatly overemphasized to the detriment of other essential mortar properties, such as workability, water retentivity, and bond strength. He doesn't mean strong bond strength, he means appropriate and full extent of bond. And those builders who strive for high or maximum mortar strengths usually obtain inferior mortar for normal above grade construction. Again, we're talking largely here about above ground construction. And you know, in the UK by the 1920s, it was asserted that you could not build a building with fat line mortars, ignoring the fact we've been doing that for 2,000 years at least. But you couldn't do that. You had to have cement in there. That was the propaganda, that was ideology, it was all sorts of things. But again, the US Bureau standards were unusual in that as long as the wall was this thick, they were quite happy for a wall to be built with a pure lime mortar, no hydraulicity at all. And this wall we rebuilt with just a 1 to 3 hot mix, no pozzolans. The only thing that stopped me building that wall was the time I had to build it. Because to build with hot mix mortars, they receive the stone, they stiffen to a load bearing immediately, really, and you can just keep building. You shouldn't go too high in one go, obviously, for structural reasons, but you could, if you really wanted, you could build the whole thing in a day with hot mixes if you had the people to do it. That is a huge quality in a building mortar. So this is dry. There's a bit of green there, but that's because we'd just taken away the scaffold that had been there all winter. The scaffold was hay bales, a big, great, and so it had been holding moisture obviously against that wall, but it's very dry now. But okay, more surprisingly perhaps, this is the modern ASTMS international standard for mortars. The workability is the most important property of plastic mortar. Workable mortars can be spread easily with a trowel into the separations, etc. of the masonry unit. Workable mortar also supports the weight of the masonry units when placed and facilitates alignment, pretty much what the other guys just said and maybe what I've just said. It adheres to vertical masonry surfaces. You know, you bust a perp joint, the mortar actually stays there. What a revelation, you know, instead of just falling straight off again, yeah? So you can press your next stone into that mortar, not try and retrospectively, well, people don't. If it won't stay there, most masons say, sod that, yeah? The point that the Reba make in that book as well, you can give the best masons in the world the wrong materials and you will get bad work. It's the materials that drive that and the potential of those materials that drive the workmanship. Because, anyway, we'll talk about that later. So, workability is a combination of several properties: plasticity, consistency, cohesion and adhesion, and I underline that because I'm like that, which have defied exact laboratory measurement. And that's what I want to say in general. Most laboratory tests for the materials we use are meaningless to us as users and to the buildings we use them on. Freeze-thaw tests. Again, the US Bureau Standards said in 1920s, that test is absolutely meaningless. Yeah? Doesn't tell us anything, actually, about what we need to know. And it's the same with many, many laboratory tests. They're in a bubble that they can talk to one another from one lab to the next, but they're not telling us anything that we need to know. And beware of this. It's very, very common. And of course, I like this line, but the mason can best assess workability by observing the response of the mortar to the trowel. Good workability is essential for maximum bond with the masonry units. I think there are a lot of professionals obviously don't understand that workability is critical to everything. They think it's something nice. And of course we've got lots of conservation firms in the UK, the masons and others of which have never used anything other than natural hydraulic lime. So they don't even know what workability is because they are not workable mortars, yeah, in my opinion. They feel like sand and water on my trowel, yeah? That's not a workable mortar. So,
I feel like cement.
The same. And well, I'm coming to why that is, but so a wall containing, this is again the ASTMS, modern, a straight Portland cement sand mortar would be strong but vulnerable to cracking and rain penetration. A wall containing a straight sand lime mortar would have lower strength, particularly earlier strength, but greater resistance to cracking and rain penetration. Now, this is the modern American standard. You know, here we are over in Europe and the Middle East, we somehow think we know more than the Americans. I'm telling you now, in terms of standards and mortars, the Americans know far more than any of us, in truth, their essential nature. And that is the legacy of the United States Bureau of Standards research done back in the 1920s and 30s that's still running through the buildings industry in the USA. I'm not saying they do this, I'm saying they understand the importance of it. Now, why is workability important? It's not just something nice. to have, because workability indicates the key property of water retentivity, which is the resistance of the mortar to letting its water go straight away into the substrate or into the air. And if you don't have water retentivity, that happens. We know, NHL mortars, they dry very fast. In doing that, they tend not to have made a bond because the water, and they are hydraulic, so their set relies on water. You put a porous brick to a non-retentive mortar, it will suck the water out of the junction straight away, and that mortar at that junction will not set properly, ever. And it will leave a capillary pathway for water to run through. The other thing is, if they're not water retentive, cement will make a strong bond, but only here and there. It leaves gaps. It doesn't make a bond everywhere. The US Bureau of Standards went through this ad infinitum in the 20s and 30s because they were trying to understand why their brick buildings of solid wall construction in America were leaking like sieves for the first time in history, having just been built with cement sand mortars. Yeah? The absence of workability affects workmanship. The absence of water retentivity prevents their ability to make a proper bond and a full extent of bond. A water retentive mortar does make that bond because it's slowly letting that water out, and suction, again, with 25 years of natural hydraulic lime use, we kind of see suction from the fabric as our enemy. It's actually our friend. It's what helps our mortars to set and to stiffen to the degree when carbonation can begin. Carbonation begins when the water content of a mortar is only 5%. But you don't want it to get there too fast. It needs to be a steady release and in equilibrium with the porous substrate. And that's what you get when you use a water retentive mortar. And that was the purpose of the US Bureau of Standards saying 1-3-12. It gave you workability in that mortar and water retentivity in that mortar. Therefore, the bond was right. Yeah. So if we look at and what they talk about, this is a cement sand repair in Canada that I undid last year, and everyone was saying to me, well, yeah, but we don't want to take that down because we haven't got any more of these tiles. They came from San Francisco in 1860. We can't, and if you take it down because it's built with cement, you'll lose them all. I lost none because not a single clay tile had made a bond with the cement. It was difficult because it's hard. You've got to be careful, but actually you just lift them out and you have what the US Bureau of Standards call mortar pancake. There's a mortar pancake. That's exactly what we're talking about. The absence of water, the water is sucked out of that junction, doesn't set properly, doesn't make a bond, therefore it's always going to let water in. And to the lesser extent, but to a relative extent, NHLs are exactly the same. Okay? And I did do it, I rebuilt it with a hot mix there, and so on. And the other thing that they talk about and that Boynton talks about is the durability of the bond. Not that the bond is durable in frost and all that, but that once that bond is made, it doesn't break, that it stays there. And this is a cavity wall construction, 1950s in the UK, so 1950s, hear that date. There is a hot mix airline mortar that it was built with. It's in perfect order. That recession is not erosion. That's how that was the style by the 1950s. Leave the mortar back a bit. And that bond is fully intact. And that building is dry. This one next door, built with the same materials but repointed with cement, is permanently wet. This one is permanently dry, and that's the difference. Yeah. So another reason that even if they haven't made a proper bond, a mortar without water retentivity will break its bond if it's hydraulic, because of the inevitable the nature of hydraulic materials. Every time a cement or a highly hydraulic material gets wet, it expands a little bit and then it shrinks. It expands and it shrinks, and it does that in every rain cycle. It also does similar in every thermal cycle. So those two things, they're unstable materials. So even if they've made a bond in the first place, they're going to break that bond. We get initial shrinkage in fat lime mortars. Some people find that irritating. But again, the US Bureau of Standards, bless their souls, looked at that too. showed that that initial shrinkage that we get in a fat lime mortar, whether that's lime putty, hydrated lime, or a hot mix lime, is in the first 24 hours when the mortar is still plastic because it's water retentive. And that, once you close that down, as you do, and you can, that's the only shrinkage that mortar will ever experience in its life. And typically it doesn't shrink, that doesn't move forward, it's a lateral shrinkage pattern. With hydraulic materials, and of course relative to their hydraulicity, they demonstrated, and we know this, we all know this, we see cement renders full of cracks, That's not because of mechanical movement, that's because of the nature of the material. They will shrink up to 4 times that same volume that we get in a fat lime mortar in their lifetimes, but only after they have set hard, when there's nothing you can do about it. So, I said earlier, I just want to say, well, these are what we do with these mortars, these are what they're for, which mortars actually meet those criteria. And I have to say, in summary, I'm not sure I've finished yet, but in summary, earth lime mortars and hot mix lime mortars and fat lime, lime-rich mortars. Doesn't have to be a hot mix. That's not essential. That's just the most efficient, economic way of making the best mortar in the world. That's all. So I'm not biased, but they don't have to be. So that's where we need to hold these mortars up to these criteria, because the purpose is surely that the building doesn't crack and that it is dry most of the time. That's what they are supposed to be, isn't it? We've forgotten what they look like in Britain, and just an extreme example of that, this is the Atlas fountain at Castle Howard. Obviously we didn't use hot mix air lines when we repaired this building, obviously we didn't, but in 1982 they filled this is on the elbow of this Triton here, they filled that with a neat cement. Logical, it's a fountain, you have to use neat cement, and the expansion and contraction of that in what we can't deny is a very wet environment, that expansion and contraction, this is Portland stone. Look at these, it's as if you chop away from that joint with an axe. It's not, it's expansion and contraction in wetting and drying cycles. It is incrementally just split that stone away either side of itself. That's what we're talking about, this expansion, contraction in wetting and drying cycles. Sorry, oh, wrong, what's happening? There's a blue thing on there. I did use a hot mix airline to repair the end of his nose, that was missing. So that's still there, even though it's just an airline hot mix. Oh, he's gone now. He's offended. Sorry? Right, okay, sorry, yeah. Okay, and if we start to look at this shrinkage in the context of natural hydraulic lime, this is Holy Island, Lindisfarne, the church on Holy Island, so a very important church, one might think. Repointed with a natural hydraulic, I know exactly which one and I know exactly when, with Astier 3.5, the softer of the NHLs on the market, it has to be said, and probably the more consistent, not always, but I hate to say it because they're the most aggressive marketers of this material in the world, but and this was done in 1999, so this is it. We're looking at something done when I looked at this 20 years before. And I think you can see that has shrunk away from every stone. So it didn't make a bond in the first place, and then its natural behavior has led to shrinkage away. And the inside of that wall, which is that thick, is bright green with algae. So that's not that's not what we want, is it? We don't want that. And of course, in situations where there are salts in the equation at lower level, the softer of the Pennine sandstone, because this stone is one of the most durable in the world, you would say, is powdering away with salt activity, and the mortars are not behaving in any way sacrificially. Okay, they can't. So that's after repointing with this is another dilemma we have. you know, that mortar that's there is in no way resembled in colour or anything else mortar proportion the original mortars of that wall. This does, and the bloody architect's complaining about it, saying, oh, well, couldn't you have matched the cement mortars in cut? Yeah, no, I couldn't. I did it like for like, you know. Why didn't you walk around the island and see these mortars all over the island still there before you decided they weren't durable? Anyway, so, and that, I hope you'll agree, that's very dry now, and that's what we expect to see when we point with hot mixes. And I'm coming into the reason why. So, when hot mix lime mortars, lime-rich fat lime mortars, don't have to be hot mix, but with at least 1 to 2 proportion, are very capillary active, and that is the key to this behaviour. Any water getting into their pore system is going to come out. Now, the fact that they're capillary active, which is the sales pitch of most NHL suppliers and producers in the UK, is, oh, they're capillary active, so when the rain hits them, they're just going to soak water right in, like they do if you put them in a dish of water, but there's not many buildings that sit in dishes of water, it has to be said. They'll say that, but actually again, because what you get in a calcium carbonate matrix is a very particular pore structure, a very particular pore size distribution, very dominated by 1 micron pores, so 1,000th of a millimetre, but those sorts of either side of that are the optimal for capillary movement. Any water that gets into those doesn't want to be there. I'm going to get out of here, and the wind drives that process. Yeah, the energy from the wind is driving the capillarity. But it's essential that you have an interconnected pore structure, obviously, which high lime rich mortars do have, and they have this, as I say, this preponderance. I'll show you the graph in a minute of 1 micron pores there or thereabouts. And so they're actively sucking water out of the fabric. And of course, that's the job of the mortar. Unless you have a render, a plaster, the mortar has to do that work. And it needs to do it in preference to the stone having to do it. Typically a more, sandstone has a bigger pore structure. It's not as capillary active. So limestone, of course, has exactly the same pore size distribution and structure. So the worst thing you can do is to point any limestone building with a mortar that is of lesser capillarity. Capillarity is the real meaning of compatibility. It's not about compressive strength, that's shorthand. And obviously the more compressive, usually the denser and the less capillary active, but not actually necessarily in the case of a high, anyway, sorry, I won't go there. Anyway. This is David Wiggins, the engineer who's one of our gang. But if you plug that, what we need to happen is any water hitting that building, and I'm sorry, I didn't finish. Yeah, the thing about capillarity, the air pressure within that pore structure will resist the penetration of water beyond about that limit. So in a capillary active mortar, received water cannot get very far. And all of us who work on building, we know this to be true. We might not have taken it on board, but we know this to be true. We spray the old mortar joints for, if it's NHL, well, for as long as you possibly can to give yourself some kind of insurance against it drying too fast. And if we dug in with a mortar pick, we'd see that the water has gone that far. We could have stood there with a hose pipe for an hour. It's still only gone that far because the air pressure within resists. And this is physics. It's not theory, not an opinion. These are the fundamental laws of physics. So that we're seeing in operation, yeah? And so, but water going in here, it needs, but water is received in other ways, obviously. And if it's in the wall, it needs to be got out as quickly as possible. So with a bigger pore size distribution, it's going to want to go into the most capillary mortar part, and that is the mortar. And that's the definition of sacrificiality, that any salts or whatever are captured in the face of this mortar. But it needs to be capillary active for that to happen. It's not enough to put something in and say, oh, we'll resist the salts. They're still there, and they're going to come out through the stone if they can't come through the mortar. So that's we all know this, don't we? But sadly, the materials we're using don't kind of know it sometimes. So this is the thing. So this is a graph of the pore size distribution in a historic hot mix lime mortar. Very high domination by 1 micron pores on either side. This is an NHL 3.5 pore size distribution. Here are the 1 micron pores. I'm just going to ask you to compare the volume, the relative volume of those capillary active pores in that mortar. And of course, St. Astier used to, I don't think they do anymore, funnily enough, but they used to have on their adverts low free lime, low capillarity, as if that was a selling point. That was a good thing. It's a really bad thing, but they're not wrong. And theirs is, as I say, the softest on the market, actually. So this does get worse, so prepare yourselves. If we then look at the pore size distribution and the porosities of an NHL 3.5 and a masonry cement, Portland cement mortar, as I once did, and I still think I was wrong. I was in an audience of 250 people, the main NHL seller from Portugal, and I asked him to explain, given that those look very similar, why they behave so differently in his opinion. But this is the point. They are almost the same in their porosity, but it's not the right kind of porosity. And in their pore size distribution, they are virtually identical. And after 20 years of using NHL in a wet climate in the UK, I can tell you they behave exactly the same as a cement mortar, not as a cement lime mortar, as a cement mortar. So, and again, in pursuit of workability, it's very common in the UK to add air entrainment. Yeah, air entrainment, do you understand that term? And as this graph shows, here we've got capillarity and vapor permeability, which is something to be demonstrated in the lab only, but has been used.
Chemical additive?
Yes, it was soap, basically. Builders used to use washing up liquid because it creates big bubbles, yeah, which they say makes it frost resistant because the expansion of an ice crystal is smaller than the trouble is, water loves to sit in big bubbles, in big pores. It'll put its feet up and read the newspaper. It doesn't want to get out, whereas it wants to get out of a very small, yeah. So, and this is just showing what happens when you add air entrainment. It increases vapor permeability in a laboratory. I mean, the test is entirely false. They suck or force air through a porous material. And usually with a vacuum on one side. Well, we don't live in vacuum, okay? And then they say it's breathable. No, because vapor cannot move of its own volition through a porous material. So, and that's the capillarity, that's the vapor permeability. I should say, if it is about vapor permeability, which it isn't, a typical hot mix has twice the vapor permeability of any other mortar in the world, okay? So if that's all it was about, they're twice as breathable. But so we've increased the vapor permeability, which means nothing, won't work, won't dry the building, and we have all but eliminated capillarity. So that is a major problem. And most masons in the UK put air entrainment into NHL mortars. Not for frost resistance, to try and get at least some workability in that bloody material, yeah? I don't know a builder, an ordinary builder anyway, who does not hate natural hydraulic lime. It seems in Britain the only people who love it are the conservators. Ordinary builders despise the material, not because it's lime, because they recognise all its problems. That's why they did, to mitigate. And they are much more breathable and much more capillary active because all of this workability, real breathability, as in capillarity, all comes from the free lime in that mortar. That's where it is. It's not in the sands. It's not in the, as some engineers say, vapor permeability is in the sand, but it doesn't work. It's the lime that gives the properties that we need, and the more of it you can get, the better. Yeah.
Because of the pore size.
That's. They didn't know that, the US Bureau standard, but that makes the better bond and everything else. So let's just have a look at a few examples. This, grade 1 listed, very important building, pointed 3 years ago with natural hydraulic lime, soaking wet all of the time. This humble little building, pointed by a local builder who's never used lime before in his life, but likes to use hot mixes, as is our experience. Ordinary builders love hot mixes. once they've discovered them, and once they trust that they will be durable. That's all they need to know. And I have to tell you, the geology of the stone is the same, all right? So you wouldn't guess that, would you, from the color of those buildings? So one is very wet, one is very dry. Other examples, though, this is cement, and this is obviously the typical pattern, climbing up to here. That's NHL. That shouldn't be happening really, should it?
No, but a bit more.
That's a hot mix building, hot mix pointed building. So again, humble, a dry one, and that one a wet one, that one a wet one. And this is what we see. And all that happens in the winter is these moisture levels will go higher, typically. You know, they don't go away ever, but they might go higher. Another little build, this is again a building just done in Helmsley, where Maria lives. Done with hot mixes by ordinary builders, because Maria makes them. You know, the park will not allow the use of NHLs. They insist on like for like, and that always means either earth lime or hot mix lime, or the two in combination. Except we drive down every time, we keep looking at this pediment and thinking, everywhere else is dry as a bone, the pediment is wet. I'm certain that they lost their nerve and bought into the idea that you needed to use NHL up there because that was more exposed. We haven't got an answer out of them. Maria keeps asking. I don't need an answer. I'm pretty certain that's what's happened. So it's nice to see the two mortars done at the same time. And this is less than a year ago that this was finished. So it doesn't take long for this moisture to start to accumulate in the fabric of these other buildings. Another one, I mean, this is a typical thing. This was done by another builder. I specified and oversaw the work and just trained them up insofar as they needed it. And they did all this work. It was done through the winter. We had bleed out from, the only place we used natural hydraulic lime was in the ridge. And of course, we're losing a lot of the free lime there is because it's bleeding out, which is the typical pattern. The hydraulic set interferes with the carbonation set. There's no question, and so it delays it. But, and so that's that. And these buildings had never been repointed with cement. They're earth lime built. I didn't perceive them to be especially wet myself, you know. That part of the range a year later, I mean, they were wet. And that again is illustrating the dynamic nature. They didn't have Portland cement, but there wasn't lime pointing at the face. And that you need it at the face so the wind can activate the capillarity. So it's a dynamic system. This isn't a passive system. This is a dynamic system when you use these lime-rich mortars. And another example with NHL, 4 years ago when I did all these photos, this building is wet all the way up. And I think the guy who was mixing it just forgot to put the air entrainment in, perhaps, is all I can say. And again, what are we going to do? What are we going to do? I did several things. I chopped out the NHL in that zone. This was taken the next day. So the day after I'd released the capillary active mortars again, that they could get to work, those bricks dried overnight. I did a panel here across the capillary rise, so I couldn't be accused of cheating. And again, when I went in the next morning to dress that mortar back, the bricks in that zone were dry. So this is a shocking thing in a way, and the same there. And you can see here, it's not only the bricks that are wet, the mortar is wet all of the time. It can't get rid of its water because it does not have an interconnected pore size and the right pore size distribution. And just to show you the longer term consequences of this was St. Astier 3.5 used in 1999 to point a Pennine sandstone, as I say, one of the most durable sandstones in Britain. This does not decay normally. And we have no sacrificial behaviour in that mortar, and this incredibly durable stone is having to behave sacrificially and deal with the salts, and the salts are breaking it down. We'd expect that when we use cement. That's in Moulton. This is where I live, around there. The only part of Britain where we have a calcareous sandstone. And this is in Acco, pointed with NHL. We understand, or premixes. The biggest problem with a lot of premixes is that they have air entrainment added. There's nothing you can do about it. They add it in there, and water repellent usually. Both of those things will destroy capillary activity. It eliminates it. So you might as well be pointing with plastic, is the truth of the matter. Except plastic wouldn't make a great bond. But anyway. So this is what we expect. Salt degradation. This is sacrificial behavior in the calcareous sandstone as a result of pointing with an inappropriate... I'm not here to condemn, but I am. Of course I am. Why do I pretend, you know? But I hope it's based on evidence, yeah? And observation and experience. But that's just a little local example. Right, okay, so let's start looking at actually the mortars they were used. There's Batty Langley, London, 1750. There are several kinds of mortar or the mortars used in buildings are 8. Not any, so inside and outside mortar made of lime and sand. Now that's the general mortar. That's for most things. Brick terrace mortar, which means trass mortar. They spell it all sorts of ways. Trass is a volcanic ash from Germany that is the most commonly used for hundreds and hundreds of years in Britain and in Holland and everywhere else for underwater works, yeah, for waterworks. Brick dust mortar, again a pozzolanic mortar. Bastard terrace made of blacksmith's forge ashes. You know, you've got iron, you've got fuel ash. These are all things that will give pozzolanic reaction, yeah. Pargeting mortar made of lime and horse dung. And horse dung was used largely because it's full of fibre. Yeah, so it resists shrinkage and so on. But this is inside chimneys, where lime plastering inside a chimney is not going to do very well because of all the pollution and so on. Furnace mortar for furnaces, ovens, kilns, so anywhere where there's real fire. Windsor loam. Windsor is around London. Loam, clay-bearing subsoil, yeah? That's what it means. And then plaster mortar made of calcined alabaster. And of course, historic gypsums are not always the same as what we use today. There were many variations, but nonetheless, that isn't for building, it isn't for plastering. In this context, this is a bricklaying book. It's for gluing decorative tiles on fireplaces. That's what the gypsum is used for, as a glue.
Interior use.
Sorry?
Interior use.
Yes, interior, yeah. And then fine mortar, so reiterating what I said at the beginning, for those that maybe didn't believe me, fine mortar, called putty, for rubbed and gauged works. That's the red rubbing bricks, the really tight jointed brickwork. Made of lime only, used on its own as a mortar, yeah? No sand, just as it is. And then if we look at the composition of these mortars, so inside mortar, 1 load of sand, 1,500 of lime. They like to mix their measures, and of course we don't fully understand, makes it difficult to compare, but anyway, mix up together as the lime is slaked in small quantities. That's a clear description of hot mixing. Outside mortar, the difference is not in the lime, not in any pozzolanic addition, it is simply in the quality of the sand. The sharpest, cleanest sand. The inside might have clay in it and so on, and they didn't care because it's inside. So 2 heap bushels of unslaked lime, so quick lime, to 1 of sand. So the quick lime, as I assume you know, doubles in volume as you slake it. So that mortar will be 4 parts of lime to 1 part of sand. Yeah, this is London in 1750. Yeah, and of course these very lime-rich mortars are all around us in this part of the world as well, with hardly any sand, and they're all around me in my village, and it's very much the norm. Trass mortar, chiefly used in walls exposed to water, rivers, ponds, cisterns, toilets, cold baths, etc. 2 bushels of hot lime to 1, so 2 lime, hot lime in that case, so it's just been slaked and then you mix it in. So it is actually a 2 to 1 proportion, in fact, not the other way. And then similarly brick dust the same and so on. These are all for underwater or underground use. And you will note, not a single mention of natural hydraulic lime, yeah? These are pozzolanic mortars made by hot mix method. And that's I suppose the moment to say, we are talking about a method,
But when was it?
not a single material, a method by which we can make any kind of material.
When was it invented?
What?
Time, no? The
How
background
far
drum.
back you can go
With
with the idea?
the hot mixing?
Yeah.
Well, the very earliest lime mortars known to us from the Neolithic period, it was for floors, hot mixed. And I would say ever since.
No, I was
Based
asking when
on
was the natural drum line?
Oh, well, it was known about then. Oh, no, it was.
Around then.
But you're not wrong. John Smeaton, the engineer, is the first one who recognised what it was. I think they just previously thought it was a really tough line.
That's what,
Yeah.
around 1700 something.
In 1756, he did that. And it did start to get used more for water work then, but not as much as we think. And if it was used, always with pozzolanic addition, never on its own.
This is pre-invention.
Yeah, I'm coming on to that, but you will see that nonetheless, they preferred to use a hot mixed pozzolanic hydraulic lime. It's more workable. The point, I would say very quickly, you can make the most hydraulic mortar you need, you know, it will set hard underwater, but with the extra lime, it is as workable as a hot mix. It is as water retentive in its early phases as a hot mix, so it makes a proper bond, and it's really workable for the craftsman or woman increasingly.
How does it dry
So,
enough to-
sorry?
How does it dry enough to carbonate?
Um,
It's in the waterworks and stuff.
it doesn't need to. No, an underwater mix. There is no free lime left.
Oh, so it's all
Carbonation is. That's the point. You're consuming the free lime. It's irrelevant underwater. So that's why they're adding with our Blue Lias hydraulic lime, which had a lot of free lime. They're putting pozzolan in to consume that free lime because it's not necessary, but it's still workable in the meantime. Yeah, that's I keep coming back to that. Workability and the initial water retentivity is essential to the formation of a proper bond that will last. Yeah. So now just a few, and shall we have a little break in a little while? Just a quick coffee break. Not like yesterday. Don't sort of everyone go out and start, and then what? Take half an hour was it or something? You know, because we. But anyway, we've got more time today. It's all right. But just a few to set the tone. So that's a British description of mortars. This is France. You know, if you believe Saint-Astier's marketing, France, the place where they have only ever used natural hydraulic lines to do everything. Completely untrue, as I will show you. But anyway, Hassenfratz, a French engineer, 1825. I should say my apprentice Emma, and I want to acknowledge the fact, was from France, but she, in the course of this, she translated many French texts into English that have never been in English. So, you know, that's her contribution to this. And in fact, many of the French texts are the most enlightening. In truth, they went into far more detail about things very often. So, in the ordinary constructions, we prefer to employ fat limes and sand to gather stones and to build walls, because this mortar is abundant and cheaper, and it takes the most sand. We'll talk about that. The most sand is 3 parts to 1 quicklime, but that's what they consider the high sand carrying capacity. NHLs and so were mixed at 1 to 1 or 1 to 2, never, you know. So anyway, because in humid places, in particular underwater, wherever we wish to stop the action and infiltration of water, we use a mortar that hardens underwater, or we use some beton. And natural hydraulic lime is typically the binder in what the French call beton, but it's concrete. That's what it means. Well, you use the term here, don't you? I heard somebody say it. Yeah, bloody French, they get everywhere, don't they? But anyway, so we differentiate mortars thus: fat lime. This is, but Chrysally, 1910, not a long time ago. Champly. We differentiate mortars thus: fat lime, used for raising walls, so above ground construction. Hydraulic lime, not necessarily naturally hydraulic, but hydraulic lime for foundations, substructures, basements, and works meant to be immersed, you know, under the ground or under the water. Slow or prompt cement for underwater works or in very humid places. Now, the distinction he's making here is calling Portland cement slow, as opposed to natural cement, which, as we know, sets hard in about 15 minutes. Nightmare to work with in many ways, yeah? You can add quicklime to slow that down. Don't need to add citric acid, add quicklime. That'll give you more working time and more workability. But anyway, so those two quotes to me are the hierarchy of traditional building construction. for most of history, and were still obviously working then. And I said yesterday, and maybe this might be a place to pause. Oh no, I'll pause there. But I fundamentally believe that traditional building technology, everything porous and capillary active, unless the stone itself is really hard and not porous, but of course the core of the wall, the mortars are, that this is the best system of building ever invented. Yeah, I mean, and the full system, where we've got plasters of the same kind inside and a render, an exterior plaster of the same material, and a lime wash, that is the full system. And it's a brilliant system. It keeps buildings dry, that it's thermally efficient, far more than we pretend. But of course, once that fabric gets wet, it starts to suffer problems, you know, and it becomes thermally inefficient. It becomes all these things. So I fundamentally believe, and of course these are sustainable. That's a sustainable architecture. It's a vernacular locally most of the time. Anyway, again from France, and Emma, who's only ever known hot mixes, of course, and she is from Calvados, when she translated this, I got "Wahey" in capital letters after, as she's translating it, because you see. But anyway, sometimes, I'd say every time, this is an engineer, because engineers are campaigning for the use of hydraulic limes from VCAT onwards, you know, for other uses, not just for underground. The crafts are resisting that campaign. That's the point. They're refusing. And this sums that up. Half the lime kilns in the region of Calvados produce natural hydraulic lime, but it just gets spread on the farmers' fields to improve the fields. Whereas the same lime is not at all used by the masons, because it does not expand as much when it slakes. That's one thing. And because it hardens quickly. Therefore, the workers would have to change how they work. It's the mirror of what the battle we have today. People are used to fast setting materials. You need to change the way you work, and you can understand the resistance. Yeah, but and then just a few to demonstrate that, because this narrative in the UK is very strong, the idea that we always used natural hydraulic limes in the past. The evidence is that we did not, and in fact that we actively did not. So when you give water to a hydraulic quicklime, it might take 12 hours for it to generate any heat and to slake. So when we see this, lime which slakes the quickest and heats the most in slaking is best, this also falls into the finest powder. The finest particle size, the greatest surface area, the maximum bonding potential with the aggregates, yeah, because of that surface area. Let stone lime, by which they mean lime made from stone, not because it's hydraulic, be chosen, which heats the most in slaking, slakes the quickest when duly watered, that which is the freshest made and the closest kept, that which dissolves in distilled vinegar, so when you put acid to it, with the least effort and leaves the smallest residue insoluble. If it's hydraulic, it would leave obviously a lot of residue. So these are descriptions of pure lime. And the idea that they didn't want it, and I'll just end on this and we'll have a break. John Smeaton, brilliant. Read his book if you can get it. The Narrative of the Eddystone Lighthouse, one of the best books about lime ever written. I mean, he was something of a hero of mine. He's been quoted against himself here. But Smeaton is saying, it is not to be wondered that workmen generally prefer the more pure limes for building in the air, because being unmixed with any uncalcareous matter, they fall into the finest powder, make the finest paste, which will of course receive the greatest quantity of sand, a maximum of 3 parts to the 1 quicklime, I would stress, generally into it without losing toughness beyond a certain degree compared to a hydraulic material, and requires the least labour to bring it to the desired consistency. It's the most efficiently prepared, and so on. Hence, mortar made of such lime is the least expensive, and in dry work above ground, the difference of hardness compared to with others is less apparent. This is then sorry, I normally swear there, this man, Henry Scott, a Royal Engineer who thought hydraulic materials were all you should use for everything, and who was, as so many in that period, utterly condemnatory of craft practice. Whatever they say, well, if the bricklayers do that, it must be wrong, because they're inherently lazy and idle. I'm going to tell you how you should do it. And that's a common thing that's going on in Britain after about 1860. So he's saying, It is a difficult matter to alter the practice of those who have grown grey in exalting practical experience and in the comfortable persuasion that the bricklayer knows best how to make good mortar and can be trusted to make it. This is just contemptuous sneering at the crafts. It's class struggle, that's what's going on. But I look confidently forward to the day in which we shall feel quite independent, as respects mortar make, of the workman's traditions. Now, Henry Scott, having liberated different workman's traditions, it went on to invent a plaster material called Scots cement, which was a mixture of natural hydraulic lime and gypsum for exterior use in the British climate. It was an absolute disaster. You know, West Kensington, all these places, all the buildings were rendered with this wonderful patented material that had finally freed itself from craft traditions, and it failed everywhere. And the reason that that part of London today is everywhere rendered with Portland cement is because of the failure of his material being replaced. Yeah. So I'm going to end that, but except to say, I have to say, in many parts of the world, this is where we are today. We're still there. We're using materials designed by chemists with all these ingredients that confound the performance of the mortar, make it not work. They're not workable. They're all these different things. So we're still there. We need to leave there. We need to start making our own mortars again, and we need the crafts to be much more influential in what those mortars are and what they need to be. Not ignore what the crafts know to be true in their heart of hearts. Yeah? Shall we have a break?